Good morning. My name is Adel, and I'm a PhD student at the University of Illinois. Today, I'll be presenting my work, HPVM-FPGA, a compiler infrastructure for programming FPGAs from hardware-agnostic languages. I will start by giving an introduction and motivation behind our work. I will then describe our contributions, followed by a case study. Next, I will give some background on HPVM, the IR that we use in our compiler, and after that, I will discuss our approach and present our results, and finally, I will conclude. FPGAs have become widely deployed in data centers like Amazon AWS and Microsoft Azure, which is making them much more accessible to application programmers. However, even with high-level synthesis, or HLS, these devices remain very hard to program from a software-centric perspective. This is mainly due to the amount of hardware expertise that is required to achieve good performance on FPGAs. Therefore, there is a need for a hardware-agnostic design flow that would allow application programmers to use FPGAs without requiring any hardware-specific parameter tuning or any hardware-specific code restructuring for FPGA performance. Our goal in this work is to use compiler optimizations to enable such a design flow. In this talk, I'll be presenting our main contributions, which are four. An empirical study showing the shortcomings of a modern HLS tool, the Intel FPGA OpenCL compiler, or AOC. 4 compiler optimizations to automate some of the required tuning, an experimental evaluation of these 4 optimizations, and a preliminary study of using design space exploration for tuning the optimizations automatically. To give a quick overview, Intel AOC is an HLS tool for programming Intel FPGAs using OpenCL. It comes with a couple of guides that help the programmer optimize their code for getting good performance on the FPGA. It also generates multiple reports that can be analyzed by the programmer in conjunction with the guides to determine how to get better performance out of the compiled kernels. Optimizations can either be in the form of pragmas and directives, or they can require significant code restructuring. And in most cases, the latter is required to get good performance. Note that although the compiler does support the regular OpenCL model of having multi-threaded kernels, Intel recommends what they call the single work item model for better performance, which basically means that kernels should be written with loops rather than the traditional model for GPUs where we have a grid of multiple threads. We performed a case study on AOC to see how much performance can be achieved using pragmas only and how much can be achieved by actually restructuring the kernel code. For the study, we used the 5-stage camera pipeline shown in this figure, and we ported the C code of this pipeline to OpenCL and created the 4 versions shown here, which we compiled and ran on the FPGA. We used the Intel FPGA profiler to get the execution times of each of these versions, which is shown in the graph. First thing we see is that by only adding the restrict keyword, we were able to get 35x speed up. As such, from here on, we consider this to be a more realistic baseline than the naive one we originally had. Second, we see that only using pragmas gives a modest speed up. But more importantly, we see that by manually restructuring our code, we were able to get a 2.6x speed up compared to only using pragmas. Note that the manual restructuring that was required here is not hardware agnostic. It required FPGA-specific tuning and techniques that we had to learn from the guides while optimizing this benchmark. This study exemplifies our motivation for a compilation flow that allows hardware-agnostic FPGA programming. I will now give a brief background of HPVM, which is the IR that we use in our compiler. HPVM, or the Heterogeneous Parallel Virtual Machine, is a hardware-agnostic virtual ISA and compiler IR. It is designed to capture the parallelism in a program using a hierarchical data flow graph with side effects, and it is able to target heterogeneous devices. Nodes of the data flow graph represent units of computation, and because the graph is hierarchical, a node can either contain plain LLVM IR or a subgraph. and edges between the nodes represent explicit data transfer between them. Each node in HPVM can have multiple dynamic instances specified using a dynamic replication factor. Therefore, this allows HPVM to capture multiple levels of parallelism. In addition, HPVM facilitates optimizations since they can be implemented as graph transforms, which was shown in the original HPVM PPOP paper. All these features make HPVM a good IR for targeting FPGAs. In this work, we extended HPVM with an FPGA backend. Our HPVM to FPGA flow comprises of an HPVM to OpenCL backend that generates OpenCL versions of the kernels. And as part of that backend, we implemented 4 compiler optimizations, which we will describe in more detail in the next few slides. The output of this backend is fed into AOC to perform synthesis and either generate an FPGA bitstream that can be used to program the FPGA or an optimization report. In addition, we have started integrating a design space exploration step using Hypermapper. This step uses the optimization report that gets generated by AOC to estimate performance and select the right combination of optimizations for a given application. The purpose here is to make the compilation flow even more automated by automatically selecting the right configuration for the optimization parameters. We present a preliminary result for this integration at the end of our talk. We developed 4 optimizations: input buffering, argument privatization, loop unrolling, and loop fusion. All of them are applied at the kernel level. And note that the optimizations are currently implemented as LLVM passes, but can also be implemented as HPVM graph transforms, which is something we are currently doing. All these optimizations are also applicable to any other HLST. For input buffering, the optimization buffers read-only input arrays in local memory to improve temporal reuse. The implementation first looks at all the pointer arguments that are never stored into, and for each such argument, we traverse the data flow graph to collect the size from the host function. If the size is a constant less than some threshold, we create an alloca for that array using the size we just found. And a loop that copies the data from the global memory array to the new local memory array is also created. Finally, we replaced all uses of the original argument with the new value we just created. Argument privatization is very similar to input buffering, but applies to arguments that are private to the kernel function. The implementation goes through the arguments of the kernel function and looks for the ones which are privatizable. If found, we create a local array for that argument using an alloca and replace all the uses of the original argument with the new value we just created. Note that a copy loop is not necessary here because the private variable is assumed to be both produced and consumed within this function. Now, in order to mark these private arguments, we introduced a new HPVM attribute called priv, which also takes a size. Because automatically determining which arguments are private can be a difficult problem requiring interprocedural analysis, pointer analysis, and array section analysis. And this has been shown in previous work. Privatizable arguments are a hardware-independent property, so this addition does not make this optimization more hardware-dependent. For loop unrolling, the pass looks for loops in the kernel function which have bounds less than some threshold and fully unrolls them. In many cases, fully unrolling outer loops provides opportunity for fusion, which is the next optimization that we'll talk about. However, we found that LLVM inserts a loop guard branch for loops with variable bounds. This makes fusion not possible after unrolling. As such, we introduced a new intrinsic called isNzLoop to mark these loops that the programmer or front end knows are always entered. The pass looks for the intrinsic and uses it to remove the guard branch for the loop which has that intrinsic in its header. And then the actual unrolling mechanism is done using the LLVM unroll loop utility function. For loop fusion, We traverse all the loop nests in the kernel function, starting at the outermost nesting level. At each level, we build disjoint sets of usable loops such that each set of loops has the same parent and bounds, no interloop fusion preventing dependencies, and no intermediate basic blocks that cause dependence chains between the fusion candidates. A diffuse analysis is used to check SSA dependencies, and the LLVM data dependence graph is used to check memory dependencies. Once we build all the disjoint sets, we recursively fuse the loops in each set one pair at a time while moving any intermediate basic blocks either earlier or later. Note that to check the legality with respect to the fusion preventing memory dependencies, the function is first cloned before every fusion, and then fusion is attempted. After fusion happens, the data dependence graph is checked to see if the illegal dependencies occurred. If they did, then we use the clone that we took to revert to the unfused version of the function, thus undoing the fusion. We devised two experiments to analyze our optimizations. Our first experiment was to study the effectiveness of our optimizations, and we performed an analysis on 8 MachSuite benchmarks and the camera pipeline from the case study. This first chart shows the results for MachSuite. The baseline, which is represented by this red line, is a version compiled using HPVM-FPGA without applying any optimizations. Each bar here shows the speedup of the corresponding benchmark with respect to the baseline, with all the optimizations applied to it. And the rightmost bar shows the mean speedup. We can see that our optimizations are able to achieve considerable speedups, with some benchmarks benefiting more than others. And we get an average speedup of approximately 4x across all the MachSuite benchmarks. The second chart shows the results for the camera pipeline. And the baseline here is also a version compiled using HPVM-FPGA without any optimizations. Each bar here shows the effect of applying one or more optimizations on the benchmark. So for example, B is for input buffering, P is for argument privatization, U is for loop unrolling, and F is for loop fusion. And when we have more than one letter, it means we are combining all these optimizations together. Our findings showed that loop unrolling, loop fusion, and argument privatization are the ones that gave the most speed up whenever they are applicable. This is shown in these bars containing the U and F and P together. And a similar result was also found when we analyzed the MachSuite benchmarks as well. Our second experiment was to compare the quality of the designs that we can generate automatically to the manually restructured OpenCL code from the case study. To do that, we compared 5 different versions of the camera pipeline. The first 3 versions are the ones we used in the case study. So the OpenCL baseline, which has restrict, the OpenCL Pragma version, which only uses pragmas to optimize the OpenCL code, and the OpenCL manual version, which uses the manual restructuring of the code to optimize it. To those 3, we added an HPVM baseline, which is the same as the one in the previous slide. And we added an HPVM optimized version, which uses all the compiler optimizations at the same time. We can see that we are able to match the performance of the manually tuned code using our automatic optimizations in HPVM. Also, by comparing the baselines, we see that HPVM did not introduce any significant overheads to the compilation. In order to automate the process of finding the best configuration and combination of optimization passes, we decided to integrate a design space exploration step into our compiler. So we present here our preliminary analysis of this integration. As a reminder, we used Hypermapper, a multi-objective capable DSE tool, and we added a client that communicates with Hypermapper and applies the configuration that Hypermapper provides to the compilation step as shown in this figure. This table shows how we modified our passes to make them more configurable and what design space exploration parameters we used for each one of these passes. As an example, we modified loop unrolling by removing the threshold and allowing partial unroll. And for the parameter, we set it as the loop unroll factor for every loop. For the objective of DSE, we used estimates of the frequency and FPGA resource utilization that are provided by the AOC optimization report. To evaluate this new integration, we used an edge detection pipeline from the original HPVM paper. This is a benchmark that was written for NVIDIA GPUs and has never been optimized for the FPGA. We also used the camera pipeline to see if we can find the same design point that we manually generated in the previous study. Our preliminary results showed that integrating design space exploration is promising. We were able to find a few good design points, giving approximately 2x speed up for edge detection and approximately 3.5x for the camera pipeline. However, we found that the frequency estimate is not a good metric to gauge overall performance. This can be seen in the image on the right, which shows the sample space for the camera pipeline. And we can see that all the design points fell into 3 buckets of frequency. Our findings showed that 2 designs with the same frequency might not always perform similarly on the FPGA due to the bandwidth and memory stalls. As such, we need a better estimate of performance, which is something we will be working on in the next step of this work. To conclude, we presented HPVM-FPGA, a compiler that uses optimizations to automatically generate good FPGA designs from hardware-agnostic IR HPVM. We showed that the effectiveness of our optimizations in automatically optimizing applications using 8 MachSuite benchmarks and a camera pipeline. We also showed that we were able to automatically generate a design that matches the performance of a manually restructured OpenCL version for the application. For future work, we will be working on a performance model to better estimate performance in the design space exploration step. We will also be working on using the data flow edges in the HPVM data flow graph to automatically generate channels between kernels to enable pipelining of multiple kernels on the FPGA. Thank you for your time, and I'll be happy to take any questions in the live Q&A session.